Hello and welcome back to Calculus 2. So we are starting the chapter 9 on power series. Now the power series goes power because of the exponent, but I like to say, power not as exponent but as a power, right? Because you can really do some powerful stuff with this. For instance, you can integrate whatever you want. You can differentiate whatever you want. You can do anything you want with anything you want, technically. So if the function is too hard to compute, if the function is hard or impossible to integrate, you use power series and you make joke out of anything, which is really interesting thing. So what happens with, what are power series? So power series are infinite series that will have a variable x inside. So you have x to the n. And they are polynomials, technically.
Of course.
So when you write the power series centered, we'll explain this later, at 0 is given by, and now we go summation, k goes from 0 to infinity, ck x to the k. So you see that now you have an x in there. Now if you go and work out the terms for this sum, the first time around k is equal to 0. So you have c subscript 0, because k is 0. And then you have x to the 0. Well, x to the 0 is 1, so we don't have to write that. Plus, the next term is c1 times x to the first power, plus c2x to the second power, that's x squared, c3x cubed, plus c4x to the 4, plus dot, 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 going to infinity. Now I hope you guys see an infinite polynomial over here, because you have a constant, then you have the linear, then you have quadratic, cubic, quartic, and so on. So they're all there. We used different letters as we went through these. So you used to say y equals, let's say, c, and then you have y equal mx plus b. Well, here is your m, here is your x, here is your plus, and here is your b. Right? If you only use first two terms. If you use the next three terms, we used to say y equals a x squared plus bx plus c. CBA. Right? Coefficients. So what you see here is a way to actually write out in one notation all polynomials that exist, right? All infinity of them. So what is a power series? Power series is the series whose expansion is going to be given as a polynomial. And we will see the actual power of this very soon. You will be able to express non-polynomial functions through power series and actually get a polynomial. Then you throw away terms that you don't want, compute the terms that you do want, and you approximate your function with that. Well, that eliminates a lot of nasty calculations in your life. And those of you who are into electrical engineering, yeah, power series are going to define your life. Further, those of you taking differential equations next semester, Chapter 3 is solving differential equations by power series. So pay attention. Chapter 9 is going to actually get you to pass through Chapter 3 in DFQ. Now, this is the first power series. Now, the one that I want to actually pay attention to is the power series centered at x equals to a. So power series centered at x equals a. So what do we have? We have a summation of ck x minus a to the k, going from 0 to infinity. If you write this out, you get your 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus ... going in forever. Now this is the one that I want to box, because if a is equal to 0, you get the case above. If you have, you know, a equal anything else, then it's centered at that, around that a. So we'll understand this story of what it means for power series to be centered at the value. But right now, all I need you to understand is that the power series, and accept that the power series is just this infinite polynomial, and that you will be taking a part of that polynomial and use it for a calculation, and then you will take in the rest of the polynomial that goes to infinity and throwing in the garbage. So now, again, the derivation of this and the proofs and all of that kind of stuff, that's all for honors part. But there is a way to show how all this progresses. It's actually in a book if you're interested. You will read it, or you can ask after class. Now, what I need to focus on here is the idea of what these power series are and which ones you have seen so far already. Well, you all seen so far the equation for linearization, or what you also call it, a tangent line. So this equation is actually the part of the power series, and it plays a role in developing power series. Guys, power series are going to be a way to compute, a way to approximate function. So you want to replace e to the x with a polynomial. You want to replace sine x with a polynomial. Because when you start getting the combinations of this, and we'll see that in 9.4, how do you integrate just integral of e to the x squared? You don't, right? You don't get to integrate that because there is no another x in front of e for u sub, and none of the other methods or techniques work. So when you see the integral of e to the x squared or negative x squared, you just stare at it and cry, because there's nothing you can do. However, if you know power series, you would express that e to the negative x as a power series, and then you are going to just throw away the terms that are, 4 or higher, or 5 or higher, or whatever. So you keep first few terms, like anywhere from 1 to 3, 4, and then the rest of the is thrown away. Now, the more you keep, the more precise of an answer you get. So ultimately, we want to use power series to replace nasty functions that need to be either integrated or calculated or something, and get the simple polynomial in its place that we can manipulate easily in terms of graphing and finding zeros with the software and so on. By the way, polynomials are the worst for zeros, obviously, but I don't know, in many minds it still beats any of the transcendental functions, right? So what do we have for this? Power series is supposed to approximate the function if you truncate some of the terms. So technically, I'm going to write as a formula that f of x is equal to the summation of ck times x minus a to the k, and then k goes from 0 to infinity. So this is equal only if you use all of the infinity. So let me write that in blood over here. This is equal only if, and now we say so this is equal only if sum goes to infinity. if we, in parentheses, for the sake of the calculation, if we, for sake of calculation, truncate our series, power series becomes, so then power series becomes an approximation. So what I'm going to tell you is that I can write e to the x as an infinite polynomial, and I will have equal sign in between e to the x and the power series. I can write sine x is equal to some kind of power series, but that's only equal if the summation goes to infinity. So if you're using all infinity of the terms, then they're equal. If you are truncating, meaning you're throwing away a certain amount of terms, or the most of the terms, whatever, you keep first 3, 4, and you throw the rest in the garbage, and the rest is infinity, then you're getting an approximation to your function. Now, the old approximations that you guys know from before are the approximations, something like the tangent line approximation. So this is actually the first two terms of the power series. If you are to recall the formula from Calc1 approximation, linear approximation. So Calc1 linear approximation. So if you have a Calculus 1 linear approximation, the formula was given as L of x is equal to f of a plus f prime computed at a times x minus a. So this is the way the formula was written in your Calc 1 class. Now, what I'm going to do is I'm going to just write a power series underneath the first terms, and I'll say C0 plus C1 x minus a. So how's this different? Right? It's the same, because you have a constant here and a constant here, and then you have x minus a, x minus a. So this over here would be first two terms of power series. So first two terms of power series. So now when I
you're my friend sheet. You're my friend sheet.
Right, so that's
my friend sits over there.
So what am I going to do now? Now I'm going to say, well, if I want a better approximation, use more terms. So linear approximation is not the end. You learned approximation with the tangent line, and that's where you stopped. But what I'm saying is you can go on and have 3 terms, 4 terms, 5 terms, and the more terms you put in, the better approximation you have for your function. So now, here in red, to make this better, this approximation better, use more terms, right? So use more terms. So what do you do? Well, if I want to approximate f of x, I can use f of a plus f prime of a, x minus a, and then in power series, we'll see later, it's called Taylor Polynomials and stuff. It's going to be f double prime of a divided by 2 factorial, which is 2, x minus a squared. So there you go. I added a term. So this one is better. this one is better than your original linear approximation. This is quadratic now. So you have a quadratic, and then you can add another term with the third derivative divided by 6, x minus a cubed, and that would be even better. So you can add as many of these terms. Now clearly, as you keep adding terms, you keep adding calculations. So it's going to be a trade-off between what is the precision that you want for the calculation, right? So how good you want this approximation to be versus how much work you are willing to put in. Now, in the era of computers, obviously, we don't care about calculations because we have machines to do calculations for us. So our job is to be able to take a look at the situation, see what the function is, figure out that we need to do power series, and then let the machine do it. Computer won't complain if you ask it to compute 1,000 terms, 10,000 terms, 100,000 terms. It's just going to take either, split second, half a second, 1 second. That's the difference for the computer. It doesn't care. So you can pick pretty much any number of terms once you start using the software. Now, the question is, how do we find these approximations? And then also, the question is, what does it mean to be centered at 0 or centered at some other non-zero value? Well, what it means is that the function is going to match and be good approximation to your function just for some period of time, right? For some on some interval. And when you're out of that interval, the function and the approximation are going to diverge from one another. So if you try to compute the point that it's very far from the center at which you are looking for power series, your results are going to be abysmally bad. So the center for the power series is very important, and it always needs to be close to the values that you want to compute. Then you know that you are getting good answers. Now, we have to use, and this is where I have the problem because, again, sections 9.1 and 9.3 should be one section. We are going to use now Taylor Polynomials. We're going to define Taylor Polynomials, and we're going to use Taylor Polynomials to take a look at, let's say, sine x first, and then maybe ln x, right, would be a good thing to do the approximation for. So what am I doing? Why is this called power series? It's called power series because I'm going to replace the function sine x or e to the x or ln x or whatever else you can come up with a polynomial. Polynomials are extremely easy to differentiate and extremely easy to integrate, and it will be much better to work with a polynomial of some kind that it's, I don't know, whatever degree you pick, second, third, fourth, fifth degree, whatever you pick, it's going to be better than working with e to the negative x squared. So that's technically it. So in order for us to get the power series, we have to define the procedure, right? And we'll give it the name Taylor polynomial when we get into 9.3. So what we are doing now is we're going to take a look at the summation. Well, sorry. F of x is equal to summation k goes from 0 to infinity, ck x minus a to the k. So this is just a standard power series, standard definition. But now what I'm going to do is I'm going to define what ck is. So ck is the kth derivative of a function computed at a divided by k factorial. So this is your ck. So you have your two formulas over here. So power series, and these are coefficients. So we have coefficients, ck, and the notation on top means this. So maybe I should, let me just clarify that over here on the bottom. So this means kth derivative of f of x computed at x equals a. Now a is also the place at which you center your power series. So you have two things going for this one. All right, great. Let's work this out for sine, and I hope you will go home and do cosine on your own to practice. This would be a standard problem for exam or something like this. So expand e to the x, expand sine x, expand cosine x squared, right, and these kind of things. It's actually extremely easy. So let's go. I define my function as, say, sine x. Now, to do the power series, what I need to do is to figure out the kth derivative computed at a divided by k factorial times x minus a to the k, where k starts at 0 and goes to infinity. So this is your setup, and if you know what each one of these pieces mean, you know, this is going to be a walk in the park. So we see that the formula has this piece which is kth derivative. So all you need to do is to take as many derivatives as you want until you get bored. So let's go. I have f prime of x, derivative of sine x is cosine x. F double prime of x is negative sine x. F triple prime of x is negative cosine x. And then now notation switches to the parenthesis. So the fourth derivative of f of x is going to be sine x. So we can, right, let's do one more and then we say, okay, it's enough. So the fifth derivative will be cosine x. So what I have here is the list of derivatives. And as you can see, I started with the first derivative and ended up with a fifth derivative. You can push this as far as you want. Obviously, you just have to have all of the derivatives prior to that point. So if you like pain, sure, go home and work this out for 120. Right? So I don't see too much enthusiasm on that one. Okay, fine. So now, what do I have? Well, function goes, right? So let's go. The sine x is going to be equal to the summation of, well, I already have that written. F kth derivative a divided by k factorial x minus a to the k, and k starts at 0 and ends at infinity. So first thing around is to plug in 0. So I get 0th derivative computed at a divided by 0 factorial, and then we have x minus a raised to the 0. So that's my first term. Second term, so plus. Second term is the first derivative computed at a divided by 1 factorial of x minus a to the 1. So you see that in this case x minus a survives, and that's the linear part, right? It died in the first one. Plus the second derivative computed at a divided by 2 factorial x minus a squared. Plus f triple derivative computed at a divided by 3 factorial, and then x minus a cubed. Plus, since I have fourth and fifth derivative, so the fourth derivative computed at a divided by 4 factorial x minus a to the fourth, plus the fifth derivative computed at a divided by 5 factorial, and then x minus a to the fifth, plus dot dot dot, going forever, right? Now I stopped at 5 because that's how many derivatives I computed. So what do I do with this? Well, we just plug in. Now, these are the definitions that you guys should know, but f on the 0th derivative computed at a is just f of a. So 0th derivative on the function is actually the original function. So that's that. And 0 factorial is defined to be 1. 1 factorial is also defined to be 1. And then 2 factorial is 2. 3 factorial is 6. And so on. The most confusion and most issues happens here. So, guys, it's a definition, right? It's a definition. So, you have 0 factorial is equal to 1. Well, so now we get to plug everything in. Now, I didn't say that we are centered at 0. I should not put that as well. So, centered at 0, which is the origin. Let's go. The original function was sine, right? Yes. Original function is sine. So we are computing sine at 0 times x minus 0 raised to 0. Right? You see how pointless it is to write all of that stuff, but there you go. I did it because I'm the best. No takers? Whatever. The next term is going to have a cosine in it, and that's when it's k is equal to 1, so still no denominator. We have cosine of cosine of what? Okay, so we do cosine computed at 0 divided by 1 factorial is 1, and then we have again x minus 0, and now it's to the first power. Plus, the next one is negative cosine computed at 0 times.
No, isn't it negative sign?
Yes, thank you. Negative sine of 0, and then we have times x minus 0 squared, because we use 2. So, plus, no, minus, we'll put in parentheses. So, cosine of 0, and then x minus 0 cubed. 2 more. So now we are at the fourth derivative. It's just sine x and then cosine x, and we're done. So sine x computed at 0, x minus 0 raised, so 0 is upper limit. And the reason why 0 is upper, whatever, we can do that, the theory later. Not 0 here, 4, sorry, 4. And then plus the last one we have is the cosine of 0, x minus 0 to the what's the exponent? 5. Good. Yeah.
Don't you divide the functions by the
Divide by 2, divide by 6, divide by 24, divide by 120.
Just be negative. negative sign.
Oh no, this is just a plus over here.
No, like negative sign with the negative person, right?
Yes. Oh, there's a minus here. I see. Yes.
I see you still not good at these.
What happened?
I see that you still not good at these.
Oh, you have no idea how bored I am to write all this out for no reason.
Give me the surface out right now.
There's gonna be a free Surface for sale,
Yeah.
like yesterday's with the iPhone.
It's called book game now, dude.
It's called what?
Book game.
Book game.
Yeah, book.
Book
Game. Game.
Oh, game. All right.
Book game.
All right. I got it.
Book game is surface.
So now you compute all of this mess. So you have sine of 0 times 1. Sine of 0 is 0 times 1 is 0. First term is 0. Potato. 0. Plus cosine of 0 is 1 times x, so it's just x. Plus. Why do I have equal over here? It's a plus. So now we have sine of 0 is 0 and kills the whole thing, so it's 0. Now we have minus, you have x cubed over 6. Plus sine of 0 is 0, right? So that kills everything. And then you have plus cosine of 0 is 1, so you have your x to the 5 over 120. So now obviously all of the 0 terms drop, and what you have is x minus x cubed over 6 plus x to the 5 over 120. Next one will be minus dot dot dot, and it goes on forever. What is this? This is polynomial that is going to mimic sine function. Ooh, this is really good stuff. So sine x is going to be approximated by x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus dot dot dot. There is a pattern there, as you can see. Observe that there is x cubed over 3 factorial and then 5 over 5. So this is your power series expansion for sine. Now, other than observation that there is always 3 and 3 and 5 and 5 and 7 and 7 and 9 and 9 and so on, what can you tell me about sine function? What kind of function is it? What do we know about sine function?
It goes above and below the axis. Yeah, that's it.
It's an odd function, yeah.
You were not Just kidding, yeah. That's pretty good. You're an odd function.
Do we see its odd function?
Yeah.
All the exponents of the, right? You were in pre-calc 2, you were asked to memorize this.
That was once upon a time.
You were asked to memorize that sine and tangent are an odd function and a cosine is even. Right?
Yeah.
And if you ask why, your professor goes, because it is.
Yep.
Because if you ask why in pre-calc 2, you gotta know all of this stuff up to this, because here is why. Here is why you were told that your sine is odd function. Its power series, that is infinite, is only going to have odd exponents and odd factorials don't matter. It's just odd exponents everywhere. That's the only thing that matters. Which fits the definition for odd functions that f of negative x is equal to negative f of x. That was the formula to test. So now we know what our sine x is. And now it's time to actually see this at we need to learn also about what it means to be centered at 0 and 2 or 3, right, and so on. Now, for that, let me see if my Mathematica is still operational on this machine. If not, we'll switch to the in-class computer. Let's see, is this working? Your license will expire on August 9th. That's tomorrow, right? Great. We got today, which is all I needed. Then I will renew this stuff, yeah. So all I need is today to work, and it did. All right, guys, so once you fire up Mathematica, you go to the little plus over here, and then you can put in the Wolfram Alpha query, and then you say graph, and then I'm just going to say graph sine x and x. I'm just going to graph those two functions. And there it is. It says plot sine x and x. And good thing that I have this on the computer is that I can enlarge this. And there we go. Please note that my approximation was centered at 0. Do you see that these two functions are the same at 0? Right? Now, what we see is that these two functions match their y values nicely between, let's say, negative 0.4 to positive 0.4, right? You would say that the blue line and the orange line are pretty well matched. If you ever took rudimentary physics, any physics course, and you heard of simple harmonic motion, that's the oxymoron. There is nothing simple about harmonic motion because it's a nonlinear equation. It contains sine theta in it. Now, it's a very nasty equation. I know because I dealt with it in graduate school, right? You get to do the proofs and calculations and expand the hell out of it to see what you can do, right? But what do they do in undergraduate physics? They say, if you have to compute this, replace sine theta with theta for small angles. What do you mean small angles? Well, I mean small angle like up to, let's say, pi over 6, up to 30 degrees, right? Well, what is pi over 6? Pi over 6 is about 3.14 divided by 6. That's about a half, right? Ta-da! See that? So if you are replacing your sine x with just x, that means that the y value of these two should be the same or close. Now, if I draw at 1/2 and 1/2 on the graph, if you go negative 1/2 to positive 1/2, you see that the orange line and the blue line are well matched on the y value. Like right around 1/2 over there, right, roughly around pi over 6, they start diverging. Is this going to be a good calculation and approximation at pi? Hell no. Why? Because pi is over here at 3.14. You see it? Because the blue line crosses through pi. That's where 3.14 is. Is the y value of the blue line and the y value of the orange line close at all? No. There's a lot of difference between the y value of the blue line, which is 0, and the y value of the orange line, which is 3.14. Right? So they're pi apart. So error is pi. That's huge. Right? So we see that this approximation of turning my sine function into a polynomial and keeping only one term, which is x, is good locally over here, and then as you go outward, the y values start diverging, and any other calculation would be garbage, right? But we are lucky that we can add more terms. So now I'm going to go back to my problem up there and say, and x minus x cubed divided by 6. So now I'm graphing 3 of these. I don't want to remove x. So now here is the graph. And when you consider the graph, you make it larger. You have your blue graph. So blue graph is the sine x. You have your orange graph, which is your x. And then you have your green graph, which is the x cubed graph. Do you see that the green graph matches the blue line longer than the orange? So what have I done? I added an extra term of the power series. Instead of using only x, now I'm using x minus x cubed over 3, and my approximation got better. I can go past pi over 6 to do approximations. Now, obviously, what's going to happen when I add another term? It's going to get even better, right? So now, I'm going to go back to the problem. I'm going to copy this and say, and Control V plus x to the 5 divided by 120. Boom. So now I added one more term, and the red line is now showing to the party. And you can see that the red line is going to be better than the previous green line. So you see that x bails over here somewhere, and then your x cubed, which is green, bails over there somewhere, and then the red one still goes on, right? So we are almost at being able to compute any value all the way up to pi. So hopefully, if I add my to the 7th power term, right, the 4th term, we could be approximating even further from where we centered our calculation. So let's just add one more term to illustrate that as well, to see that, again, the more terms you add, the better approximation you have. However, you are not allowed to leave the region where your power series is centered. So now here we go, and Control V, the next one is minus x to the 7th divided by, oh, holy nightmare, 7 factorial, 6, so 250, 720, 720 times 8, that's a lot. Let me see, if can I do 7, I should be able to do 7 factorial there, should understand it. And just work it out. There we go. Beautiful. I think it's the purple that is joining the party now. And as the purple is joining the party, you can see that purple almost hits pi. Almost. It's not hitting it quite, but it's almost hitting the pi. That means that if I introduce the 9th term, it will probably go very close, or if not close to pi, right? So what we learned from this exercise is that power series will take any function and turn that function into an infinite polynomial. Then you will make a decision of how many terms you want to keep in your calculation. In this case, you see, which is the case for every problem out there, that the more terms you keep, the more precision you get with your approximation. We say that your power series converges to a function, meaning that you have some function and then the power series just traces over that line, right? And you can't tell them apart. And you can't really tell them apart. If I erase the first few and just keep the last one, so kill all of this right there and push enter. And then you take a look at the blue and the orange, blue being the original function and orange being, right? You can't tell them apart. From negative pi to positive pi, you can't tell them apart, right? Because we used, and that's just using 4 terms, right? If you want the exact match, one on top of the other forever, you have to use all infinity of terms, right? So good luck with that. But it's pretty good, you know? So now you start playing with this and seeing, okay, can I get the full period of sine? How many of these terms do I need? Really, 4 are covering almost, half a period. But no, actually it covers the full period because you can start here, right? So if you have 5 terms, you would have a full period of sine covered for calculations. Now, guys, that means polynomial replaces your sine x. Polynomial of the, obviously, of the 9th degree replaces. Actually, we can quickly add that in. So, minus, now next one is plus, x raised to the 9 divided by 9 factorial, enter, and this should curve, and there you go. You see now it's past pi where they differ. So if I use 5 terms, which is going to the polynomial to the 9th power, you can't tell them apart between negative pi to positive pi. And that's a full period for sine. So now I can calculate anything I want. Also, it is easy to differentiate or integrate. Yeah, I know that the derivative of sine is cosine easy, right? But when you have some trickier functions later on, or you get functions that you can't integrate at all, like e to the x squared, right? You will replace your e to the x inside the integral with the polynomial function, and then you will decide, okay, let me keep 2, 3, 4 terms, 5 terms, and then you are integrating polynomial. Now that there is the infinite gains, right? Because you have replaced the function that you can integrate to begin with a polynomial that you integrate like that. So, and that's your 9.4. Which is tomorrow. So now I would like to challenge you to give me a 3-term expansion for ln x. So I'm going to ask you guys to give me expand f of x equals ln x, and we are going to expand at 1. So expand at x equals 1, give 3 terms. So now when you're doing the formula, instead of writing x minus 0, you get to write x minus 1. Please use common sense. Ln function has a vertical asymptote at 0. I can't expand around 0. Function is not defined at 0 at all. So I have to expand elsewhere. Now Since ln I know it goes through 1, let's expand around 1. So you need a little bit of derivatives, right? And how many derivatives do you need?
3.
Nope. 2. Because the first term is the original function, which is ln x. You have that. You just need 2 derivatives to get your...
But I can't, but you know what that one is, though. I'm doing it now. What's one break? Watch now. I've done it wrong. I'm just gonna stop this now. Well, I'm just going to do the start. Finals. Yeah. That's the goal, right? Everything there, so I got to study or something. Yeah. Back.
To Calc2, huh? You're probably doing the project because you're very quiet.
I'm doing the project.
No.
Calm down.
I caught you? No, it's good you're doing the project. You can watch this video later.
I hate Microsoft Word.
You can use the Gmail's free version of it.
Yeah, you can use. Oh, this has it. Word docs. Trying to put everything into the radical and takes the first number and just misses everything. Oh yeah, so I got your parentheses. I heard you, bro. I heard you, bro. Very clever man. I heard you. You're faithful. You love you. You must appreciate you. Pretty good, bro. So all my. That was the nicest put down I've ever seen.
Nicest. Oh, I'll have to pay. Give me some time. All right, so here are the 2 derivatives. So function and 2 derivatives are giving us first 3 terms. Now, it's centered at 1. So when I start my ln x is approximated by, I go function, which is ln x, but it has to be computed at 1, plus, what happened? No, first term is raised to the 0, right? X minus 1 raised to 0, so it's not there.
Oh, so
second term.
The centering doesn't like dictate what the echelons are?
No. So now we have 1 over x, which will be 1 over 1 divided by 1 factorial times x minus 1 to the 1. And then plus, the next one is, again, 1 squared, so it's going to be negative 1 over 1 divided by 2 factorial, and then we have x minus 1 squared. Now, this is 3 terms. But then you look at this, and the first term is going to be 0. Because the first term is going to be 0, yes, the third derivative. So it's not, we need 3 terms, so you do 3 derivatives. It's we need 3 terms, you do 2 derivatives, but because the first term worked out to be 0, or if any other term works out to be 0, then you have to add terms. Because clearly, when the first term is 0, then you only have 2 terms in your answer, and the question is to do 3 terms. So we are going to do now one more derivative because we must. Yes?
So the k on the bottom of the summation is different than the k's. No problem.
They're all the same k. It's the same counter. It's 1 zeros everywhere, 1 everywhere, 2 everywhere, 3 everywhere.
But it's like if it's centered at 1, why doesn't it? Does it just it always like the k, like the kth derivative is always.
Look right here.
You know, I know.
You see, it's the center of 1 goes here and here. Has nothing to do with anything else.
I'm talking about the exponent. Like the exponent.
Exponent, well, is 0 over here, so no x. It's first power over here, second power, third power, so it goes 0, 1, 2, 3.
Every time, like regardless of the centering.
Yes. Regardless of center. Center has nothing to do with it. Powers are driven by k's.
The k on the bottom is not the center, so this one wasn't k equals 1.
Exactly, it's not k, it's a equals 1.
Oh, okay, got it.
So now I need to add one more term, and that's going to be 2 divided by 1 cubed is 1 divided by 3 factorial, and then x minus 1 cubed. So what do I have ln x to be approximated by? The first term is 0, plus 1 divided by 1 is 1, 1 factorial is 1, 1 divided by 1 is 1, so we only have x minus 1 over here.
Sound like one of those announcers at like the auction. You know what I'm talking about?
Yeah, I do.
That's not how they sound, but
Negative 1 half x minus 1 squared plus, so you're suggesting I should quit this and just go and announce stuff.
Go sell like horses or something.
Go sell horses.
wow.
Okay, got it.
That's enough.
I'm around my neighbor's
It's an upgrade. Well, technically, salary-wise, anything is upgrade to doing this job. So, yeah. Exactly. I will never meet you, man. Yes?
How come ln, the first ln that cancels to 0 is ln of 1? Because wouldn't it be...
The first term is ln, it's f of a, right?
Okay.
So first term is f of a. You see how the first term is f of a?
Okay.
So that's original function, and then you go with your derivatives and have fun with that.
Okay.
So f of a and a is 1. So finally, ln x is approximated by x minus 1 minus 1 half x minus 1 squared plus 1/3 x minus 1 cubed, and that's the 3 terms. Now, you can go calculate the next one and the next one and the next one, but that's good enough. Now, also what you can do here is you can go and you can expand everything and add like terms and just get the cubic polynomial with 4 things, but I mean, we can do it, but why? This is good enough. Yes?
So we need one. So 0 doesn't count as a term?
No.
Okay.
So that's why we had to do one extra. So for sine and cosine, every other term is 0. So if I'm asking for 4 terms on a sine or a cosine, you have to do 8, right? You do 7 derivatives plus the original for sines and cosines, because every other is 0. We did the sine, and you see how every other one, first and the third and the fifth and then the seventh.
We only ended up with 2.
Yeah. So if you did the first 3 terms, you would get these guys.
We have to do. Oh yeah.
You see that? So you have to be careful. You do enough, so it's always whatever I ask for, number of terms, you do number of derivatives, number of terms minus 1, right? That's it, because you have the function to fill in the first term. But if any of those terms are zeros, then you have to add derivatives, and you have to go pass.
For sine, we just have to take the sixth. No, the seventh.
Seventh, yeah, for yeah. Great. Now again, why is this good? Well, this approximation here is a polynomial calculation that you can do with a stick in the sand, right? And you do it with a stick in the sand, you can calculate the ln of 0.9, ln of 1.3, ln of 1.275, right? So anything that is close around 1, because your power series is centered at 1, so this approximation is valid a little bit to the left and a little bit to the right. The more terms you have, the wider a little bit to the left and a little bit to the right becomes. You've seen that with the sine, right? As we added terms, more and more was matching the function. So it goes for every function we have. So can you compute ln 10 with this? No, you cannot. But you can compute very nicely approximate ln of 1.73, right? And you are approximating that well because you are using. Now, again, do you need ever to approximate using this? Like you spend 15 minutes deriving this, and then probably another 5 minutes to expand everything, collect like terms, add all the fractions, so that you can plug in 1.75 for x and compute it. Hell no, you pick up the calculator and you have the answer. Right? It's not what it's used for. This is used for the situations, as I mentioned, where you don't have other options, which is pretty much all the time when you're dealing with very complicated nature functions. Right? So you are not going to have a basic polynomial model things that are used to build airplanes. It doesn't work. You have some complicated stuff. Yes?
So this would be helpful, I guess. So we could take the integral of what we get here, and that would translate the integral of the, like that's.
Yes, but you also have to be very careful, because if you have so if you have your bounds on the integral to go from 1 to 10, it's not going to work, because this is going to be a good approximation at 1, and when you compute that limit, you are going to get pretty much the exact value. But if you compute and it's one integral, right? So when you compute at 10, it's going to be garbage, so you can't use it. This is going to be for the integral that has a small increment in energy or whatever, so you want to compute exactly how much more energy you get and what you have to trim and stuff like that in engineering. So you have your integral to go from maybe 1 to 1.7, right, or 1.5, and then this is working fine because you don't know. Again, you plug all of this in the computer, so it's pointless. But the thing is that certain functions cannot be computed. So even if you plug them in a computer, it doesn't work. And there are, guys, courses upon courses upon courses that are building up on this. So when I was selling Chapter 9, I told you, if you want to survive Chapter 3 of your differential equations, you better learn this stuff, because, that's what it is. It's called solving differential equations using power series, or power series solution to differential equations. But when you move on from this, and if you pursue mathematics and engineering and do the higher engineering, you might run into a course that's called asymptotics 1 and 2. You have nested power series in that thing. That course is, every problem is power series. And then you have nested. If you are going to do any kind of numerical course for mathematics in terms of numerical analysis and stuff, that pretty much 70-80% of that course is power series expansions. So this is used in industry a lot, because the functions that you have in industry are nasty. you get the cheapest possible functions that you can think of in your physics class. And they still let you write the formula sheet and bring it in, right? And then look at that formula sheet during the exam. And then you go in a lab and you do the computer simulation. I don't even know why they have physics in school. It's completely pointless at this point. Because I see students in my class writing the formula sheet. I get 1 page of formulas. So what are you learning in the class? Formulas in physics, and the concept to which that from which that formula is derived is all you learn. And then when you go into the lab, instead of actually dropping the ball and running the cart and doing something, you push go on the computer simulation and record the numbers you get on the screen. Just can the whole thing. It's waste of time and money. You are not doing physics at all. Right? You are copying things off of the paper and run computer simulation. It's a video game, so yeah. Nice. Collect $700 per pop. That's good, I guess. I don't know. Keeps the college rolling. But when you start working, you kiss all of that goodbye. All of your functions and everything else is going to be in professional papers and things that were discovered. But calculations for that kind of stuff, you're going to do some numerics if you are working on the high-end engineering, not the low-end engineering. Or when you say C's get degrees and then you get your electrical engineering degree with negative 2.3 GPA, and you end up in sales with electrical company because
How you get a negative GPA? Teach me.
You tell me, man. I don't know.
Teach me. You could figure that out. You broke the system.
I broke the system.
Zero, so
No, the first.
numbers, like,
No, the first time I see that the high schools are giving a GPA over 4.
yeah,
It's like, okay, you're better than perfect, right?
Again, I don't think it's you got a 4.0, you got an A in gym, and it counts towards the GPA.
My gym always counted towards GPA. That's good. It should.
that's the best.
Have less people like me around.
Well, right?
Yeah, which means more food for everyone.
My boy.
Anyway. Guys, that's Power Series. I hope you are not disappointed. You are going to take... Now, let me just see. No, I think error is in the next section, so... It logged me out. Let me just check real quick. So we did this. There are Taylor polynomials. We already discussed that. And... Is there anything else? So they also do sine and show you some of these graphs. Approximating with Taylor polynomials. Now they want you to do e to the x, blah, blah. Okay, if you have sine example and an ln example, e to the x is the easiest of all, so you should be able to do that on your own. Aha, remainder. Good. So a remainder is also here. So guys, I said the more terms you add, the better the precision. And precision is actually really pushing more terms into your expression. Now, where is the error? Error is everything that you throw away. Now, the fact is that most of the error is concentrated in the first term you throw away, because that term, right, would make your function perform much better if you kept it. You throw it away. So anytime, whenever you make the cut, 4 terms or 10 terms or whatever, the next term, the first one you're throwing away, carries most of the error. So it's enough to just compute the first term you're throwing away and claim that the error is about, and then you just state that number. All right? So let's take a look at this in reality. So actually, let me just write the error. So error. Most of the error due to approximation is concentrated in the first term we throw away. So the Rn of x is f of n plus 1, right, the derivative, computed at value c divided by n plus 1 factorial. This is the next term, x minus a to the n plus 1. Right, this is the standard. So you see it's a derivative, but it's just the next value divided by the factorial, which is the next factorial, and then you have your x minus a to the next power. So if I want to compute the error for ln x, right, I would just go and get the fourth term, and it seems that the fourth term over there. So ln x error would be given as 1/4 x minus 1 to the fourth, right? Because that will be the next term if you look at the pattern that you have. The pattern is 1/1 x minus 1 to the 1, 1/2 x minus. So, oh, and it's negative because it also has plus minus plus minus plus minus alternates. So now what I want to do is I want to use ln x. So use ln x expansion to approximate ln of 1.53. So that means I get to place 1.53 in every single one of these. So ln of 1.53 is approximated by 1.53 minus 1 minus 1/2 1.53 minus 1 squared plus, oh wait, yeah, plus 1/3 1.53 minus 1 cubed. We go and compute this. This is 0.53 minus 0.53 squared over 2 plus 0.53 cubed over 3. Now I'm going to use Abacus to compute this. What do I get? Yes. 3 minus 0.53 squared divided by 2 plus 0.53 cubed divided by 3 norms, and that's equal to 0.439176. That's fine. 6 decimals, right? Error would be about 1/4 of 1.53 minus 1 to the fourth and a negative. So now I compute that as well. I have 0.53 raised to the fourth power, everything divided by 4, and so error would be about negative 0.019726. So that's the error. Now what I'm going to do is I'm going to punch ln 1.53 in the calculator. So now calculator gives me 0.42562. 1, 2, 3, 4, 5, 7, so 8. This is what calculator gives me. Right? Now I'm going to subtract from the calculator value what I had in my approximation, and that's 0.439176. So this is my approximation. So I have 0.42528 minus 0.439176 for the error of negative 0.013908. Look at that. These numbers work too well. All right? You want better numbers? Use more terms in the original approximation. This will also be higher, which would lower your error. More terms you use, less error you have. You have to have that. So you see that the error between the, right, so again, error is approximated. Why? Because we approximated error with the fourth term, and then we still threw away infinity of the terms. But you see how good that actually is. Even though I'm throwing away infinity of the terms, first off, I threw off infinity of the terms to get this answer, which is already pretty good because I am 1 cent off. 1 cent off. So, right? I'm 1 cent off if I just keep first 3. If I keep first 4 or 5 or 6, this gets better. Now, error is telling me that it's about 2 cents, right? Should be the error. But the error that I actually get is 1.4, so a half a cent off on error. These are negligible, guys, if you're making some other stuff. Now, obviously, if you're working on particle physics, you're going to carry this out to 15 terms, and you're going to have 7,000 decimals, right? So you are going to, the application governs how many terms you get to keep. Now, obviously, on your exam, I tell you I want 3 terms or 4 terms, right? And that's that. And then you just go and you calculate extra term for error and say, I expect error to be so much, right? So note this. If I go to my to my approximated answer, and I subtract error from it, I'll get close to this number, right? So if I go to 0.439176 and I subtract 0.019762, no, 7262, and I hit enter, I get 0.41944, right? So you see that that's very close. That's only 0.6 cents away, or half a cent away, right? So you can use the error to correct your number even better. But that's actually equivalent to adding a term, right? So, of course, you are getting better. You just added the error in, which is actually the next term. So there you have it. When you see a tolerance on something that is machined, or if you're into electronics, you know that the electrical components like resistors and capacitors and so on have a tolerance on it, right? The tolerance of either given in percent or in ohms or capacitance, whatever. You guys can see that the tolerance is there. That's that, right? That's that stuff. So, yay. It's time for a break.